Hello everyone and welcome back to another video. Now this is going to be the HD7970 Lightning PCB overview video, and this time I'm gonna use a picture on my tablet instead of showing the card in real life, because while seeing the card in real life is a nice thing, I do want to bring some information over, and when I just say it and not put it on the screen, I think it's pretty easy to miss. So I think from now on for PCB overviews, like there's still gonna be a first look video for every card that's interesting, but for PCB overviews I think I'm going to use pictures from now on. And yeah, so let's get started. So this is the HD7970 Lightning. Made a video about this already, like I got it as broken. I thermoshocked the core. It works now again. Though the overclocking on it is not great because the capacitors are likely toast. But that still doesn't change that this PCB is very interesting, and if you should pick one of these cards up, they will probably perform a lot better than mine. So the VRM on this thing is quite similar to the GTX 580 Lightning. In fact, it's using the same MOSFETs, at least. Yeah, like not just vCore. So let's start by the vCore VRM, which is this giant block over here, controlled by this controller. This controller is a CHL8228G. This is an 8-phase controller, and it is running in 7+1 mode on this card, from what I can tell. Now, we do have a lot more than 7 inductors, or like a phase's worth of components, because this is actually a 14 phase being doubled by these chips right here, and these are IR3598s. Now the IR3598 can both run in dual driver and doubler mode. I actually don't know for a fact what it is using on this card, but I do think it would make sense to have them in doubler mode. So yeah, this is, I think there is a very high chance, like it wouldn't really make sense to have them in just dual driver mode. I'm pretty sure these are running in doubling mode. So yeah, that's how we get a 14 phase. And actually, if you were wondering, since we have 2 phases over here for our memory, and we just have a 7+1 because the CLJ8228G also controls the memory, we have another IR3598 over here, which seems to be doubling the +1 aspect of the controller into our 2 memory phases. So let's get into the MOSFETs that we have. So vCore, memory, and VDDCI, which we're going to get to later, use the same MOSFETs on the card. And if you know this package, you already know that these are IR direct FETs. Specifically, the high side MOSFET is an IR6721. And the IR6721, well, it's a high side MOSFET. It's that's all the interesting stuff about it, in my opinion. And our low side FET is an IR6725. And the IR6725 has 1.7 milliohms of RDS on at 10 volts gate to source voltage. If you lower it down to 4.5 volts gate to source voltage, it gets a bit worse. It's sitting at 2.4 milliohms then. I do not know what the gate to source voltage on the card actually is, but I'm guessing it is between 7 and 10 volts. So it is going to be around the 1.7 milliohm number that is listed in the datasheet. Now the IR6725 has a rated continuous drain current of 170 amps at case temperature, like the temperature of the MOSFET casing at 25 degrees. And so let's put that here, TC 25 degrees, and I should make this thing a bit thinner. And then it has a rather small, like relatively small rating of 28 amps at T ambient. So ambient temperature 25 degrees Celsius, which means that the MOSFET is just without a heatsink on a copper PCB in a box that sits at 25 degrees. And it also goes down further to 22 amps if that box is then set to 70 degrees. And all these current measurements are for 10 volt gate to source voltage. They're, well, it's what was listed in the datasheet. And it's probably also what close to what this is running. There are two LDOs, right? Like there's one here and then there's one more on the back. These are probably supplying the gate drive. I haven't measured it, so sorry on that part. I should have done that, I think. But yeah. So the memory is using the same MOSFETs. So is our one-phase VDDCI. Nothing special really. Like same MOSFETs, same thing. VDDCI is controlled by this controller right here, which is a UP1509P. Am I getting that right? Yeah, it's a UP1509P. I couldn't get a datasheet for this one, so I have no idea what switching frequency this can run at. And speaking of switching frequency, I forgot to mention about the CHA8228G. So I've listed it as an 8-phase controller. It's running in 7+1 phase. And it has a rated switching frequency from 200 kilohertz to 1.2 megahertz. If I would guess what this runs on this card, I'm guessing this runs at 600 kilohertz, going into the doublers, which means that at the phase you get 300 kilohertz, because the doublers cut the switching frequency in half. And that's gonna be that. Like I think 300 kilohertz is pretty typical for a graphics card VRM. And let's label our VRMs a bit more. That you can see everything. That's our VMEM. That's our VDDCI. That's our vCore. Now I should make it a bit thicker, I think. Yeah. Okay. And that's pretty much the VRM of this card from a component level perspective. And let's talk a bit more about the PCB. Specifically, I want to talk about the output filter for the card. Because I've just made a video about the HD7970 Matrix, which is the competition for this card from Asus. And I voiced my disappointment in the vCore output filter of the Asus Matrix card. Because the entire output filter of that card is just 10 820 microfarad through-hole aluminum polymers and a couple multi-layer ceramics, just like these ones. Now this card, oops, that was too much. Now this card has a much better output filter, and it doesn't look like much on like the first look. But the thing is, on the back, right here, you have the same thing again. So you only see half the output filter from the front. And yeah, so let's compare the output filters. So these are 400, and now I should make it thin again. These are 470 microfarad SMD tantalums. You can see that by this plus marking right here. That's a dead giveaway that these are the infamous pause caps, and these are SMD tantalum capacitors, not SMD aluminum polymers. These are tantalums, which, if I remember correctly, means these have a better ESL spec and a slightly worse ESR spec, I think. Correct me if I'm wrong on that. But basically, these are the next more expensive type of SMD capacitor over the SMD aluminum polymers. that you usually find on cards. Now, and the card has 9 on each side, so 18 in total. Now, if I remember the numbers correctly, not counting the multi-layer ceramics, that's 8,460 microfarads in total. Now let's compare that to what the Matrix has. The Matrix has 10 820 microfarad aluminum polymer through-hole capacitors. Now, these are not tantalums, these are aluminum polymers, so that's a downgrade. And these are not the SMD package that you can see right here. These are on the Matrix, these are through-hole capacitors. So some are, no, that's not what I wanted. So these are like these, your typical can types that go through the PCB with their legs. And well, that's pretty easy to calculate. That's 8,200 microfarads in total. Again, not counting the few multi-layer ceramics that are in between. So what we can see here is the Lightning not only has a better capacitor type, it also has more total capacity. Which, from my perspective, just means that the Matrix, like the Lightning, is just a straight better output filter. And I'm not even counting the thing on the back. Now, I think I don't have a... Yeah, I don't have it attached on the picture. Like, you can sort of see it up here. That's something that MSI calls the GPU reactor. And it plugs in behind the core into these connection points right here. And basically what it is a little add-on PCB that has 8 more 470 microfarad aluminum polymers, I think. They do not have the plus marking. I do not know how to read the, like how to get the spec from SMD capacitors of this package. I only know that the plus marking means that they are pulse caps and they have to be tantalums. But the ones on the GPU reactor don't have this marking, so I don't know if they are tantalums or aluminum polymers. I guess they are aluminum polymers. So they are like one tier down, but yeah, that's still 8 more 470 microfarad capacitors right behind the core. I should add that it's right behind the core. The closer your capacitor is to what you're trying to power, the more effective it will be. So yeah, and I'm not even counting that when comparing to the Matrix. So yeah, the Matrix might have 2 more phases. Like it might have a VRM that can deliver more current than the Lightning, but the Lightning just has a significantly better output filter, and I think that will ultimately make the Lightning win in a assuming everything else equal. So yeah, and let's look a bit more at some more features of the card. Here we have a dual BIOS switch. You can see there is an LN2 BIOS and a normal BIOS on this. As to what the LN2 BIOS does, I do not have LN2, I can't really test it. But it probably removes certain, like it might remove over temperature protection, might remove overcurrent protection, maybe just, like I'm pretty sure it removes cold boot bugs, like code bug problems that are fixable in software. I am not certain if it will remove any protection mechanisms. There may be, like on the 580 Lightning you had a switch for that. This card does not have any switches on the back. So it might be a BIOS side thing. You might have to hard mod this yourself. So yeah. Then, since this is an MSI Lightning card, we have our voltage measurement points right here. If you get the card in like new condition, if you get it in the box, there's cables there which can hook up to multimeter probes. I do not have the cables for any of my, like I have several, like it's not just Lightning cards, Hawk cards, and like some of MSI's higher performance cards to also have these read points. I didn't get the cables for any of them, and honestly, I wouldn't use these voltage read points. Like you can see, this one's for PLL, this one's for memory, this one is for GPU. Honestly, I wouldn't use these. I would just find my own hookup point, like behind the core for GPU, or like at this or this memory chip for memory. So I get the most accurate voltage reading, because you don't know what path these measurement points take. And yeah, so I would rather just find my own hookup point. It's nice that they are there. It's a quality of life thing, and if you don't super care about accuracy, you can use them. It's just that I do not really like to use them, but you might actually be forced to use the GPU one, because, well, this entire area is going to be covered by the GPU reactor. So yeah, you might not really get into the core area for measuring. So yeah. Then one more notable thing: there is a fuse, which I can't see on the picture. I guess it's a 10 amp fuse on the PCI Express slot. So if there's a short circuit, your motherboard will not be overdrawn. Yet the 8 pins are not fused. There is no fuse there. So yeah, those are not fused. If you have a short there, you better have a good overcurrent protection in your power supply. And yeah, one last thing would be, I think this is it on the back. You can't really see it on the front. It's slightly obstructed by this capacitor. What I have a suspicion that this is an I2C hookup point. So this is not an NVIDIA card. This means that this card is probably very much not completely analog. This is a Radeon card, so this probably has some digital functionality. That means this probably has an I2C interface, and if you have something like an Elmore EVC, which hooks up to I2C, you could theoretically just control the controller and make it do what you want without having to do any crazy hard modding soldering to it. I am not completely sure that this is an I2C hookup point, but it very much looks like one. Like your 3 pins and then your one like square pin, which I actually don't know if that's ground. But yeah, this is like what the I2C hookup points look like on other cards where I know for a fact it's an I2C hookup point. So yeah, if you have an Elmore EVC, I do not. You could theoretically just hook up to the controller and just set everything you want. Set load lines, set overcurrent protection, set voltages, maybe even set switching. Like, it depends on what the controller is capable of. Like, sometimes switching frequency is set by a resistor, then you won't be able to change it over I2C, but maybe it's digital and then you can change it. So yeah, that's pretty much it for what I wanted to say about the PCB. I think I can, yeah. In software, this has voltage control for core memory and, like, it's labeled auxiliary, which I think is VDDCI. I do not think you have PLL over voltage support in MSI Afterburner. So if you take this card on liquid nitrogen, or maybe even just dry ice, and you run into like screen signal issues and that sort of stuff, overvolting PLL can help. It depends on how the card behaves. I do not specifically know how HD7970s behave when they're cold. But yeah, I do not think you have PLL over voltage support in MSI Afterburner. Yet you may have it if you have a copy of MSI Afterburner Extreme, which I do not. But I'm pretty sure there's an MSI Afterburner Extreme version for this card, which will basically give you sort of the same kind of control you would get if you hook up to that I2C port. And yeah, so that's pretty much everything notable about the about the PCB of this here graphics card. Guess I'm gonna go a bit into what my specific card runs. Now, I said before that I have a strong suspicion the capacitors on my card have taken significant damage because the previous owner of this card baked it back to life 2 times in an oven. Not with a heat gun like I would do it, but in an oven, which means that the entire PCB, not just the core and memory, were heated. And capacitors absolutely despise heat, and they degrade very, very rapidly if you heat them up too much. And I think that's exactly what happened, because the this card just doesn't clock good. To be fair, the core has like an ASIC quality of better than 7%. So this is a really low ASIC quality core, which means that this one might just need a lot of voltage or cooling, and then it's gonna run fine. But running the card in sort of stock condition with the heatsink, that is very, very powerful. It's much more powerful than the Matrix card. This core just doesn't clock good. Like it doesn't do 1200. Unless you set voltage to 1.35 volts on vCore, at which point it just suddenly jumps up to running 1267 MHz stable. And it's like not a gradual curve, it's just like you cross a certain voltage threshold and the clock just jumps up in stability. It's not a smooth, linear line of scaling. So I've heard from people that this is how their cards behaved too, but I do have two, like I have the Matrix and I have a 7950, which is using the same GPU just with less cores. Both of these did not have that behavior, they scaled like I would expect them to. So yeah, I don't really know what to believe now, but I'm staying on my theory that the capacitors on this card were significantly degraded by the heat in the previous owner's oven, which means that the output filtering for this card, which on spec is really, really powerful, because of that degrading of capacitors now actually turned into being very, very bad, which means that there's probably a lot of voltage ripple there. I said before I wanted to hook an oscilloscope up to this, and I still want to do it, I haven't done it yet. But yeah, when I'm hooking up that oscilloscope, I am expecting to see a lot of voltage ripple on this PCB, which wouldn't be there if the capacitors would be in good shape. And a lot of voltage ripple means your minimum voltage is gonna be trash, which means you're just gonna need a lot of average voltage to bring that minimum voltage up to the level the card needs to run stable. So yeah. And then the memory part of this, I actually haven't maxed out the memory yet, but my specific card is running on 2 gigabit Hynix MFR, and from what I can tell, this is not great. So my 7950 also has 2 gigabit Hynix MFR, and I do have software voltage control for memory. I can set it up to 1.7 volts. Sadly, the memory gets worse. So the memory clocks better at 1.6 volts than it does at 1.7. Which sadly indicates that Hynix 2 gigabit MFR has negative voltage scaling, which means overvolting and very possibly cap modding will not bring you any extra clocks, which is very unfortunate. It is possible that this will scale a lot with cooling, which I hope. But so far I can tell that getting 2 gigabit Hynix MFR is not a good thing. My Matrix card does have 2 gigabit Hynix AFR instead. I haven't tested voltage scaling on that yet, but I hope that it is better than MFR. But I mean, so far DDR4 8GB AFR was awful, and GDDR5 1GB AFR was also awful. And then I hear GDDR4 4GB AFR was kinda decent, but I've never used it myself. So I don't know if the AFR family name can mean something good or bad for my 7970 matrix. Yeah, but I do want to leave it here. So yeah, I don't want to drag this out too much. So thank you all for watching. Hope you enjoyed, and until next time, goodbye.